Hey, BC Calculus, Mr. Ellinger here, and today we're going to go over the area of polar regions. Good luck in basketball. Hope it's going well. Here we go. So, how to find the area of a polar region? So it'd be like how to find the area of this curve altogether. All right, here we go. Well, the old ways are not the best ways because the old ways are dividing it up into dx's or dy's, and our curve isn't going to be defined in terms of x or y. It's going to be r defined in terms of theta. So like this is not going to make any sense. So cutting with rectangles is not going to be very, very helpful. I mean, what is the height of this thing? I won't know because it's going to be defined in terms of r and theta. So instead, I'm going to divide the region differently. I'm going to divide it into little sectors. And so on. So this would be like theta 1, and then theta 2, and then theta 3, and so on. And we keep going around the circle. So, all right, so how do you find the area of a sector? Well, the area of a sector is a formula that's basically comes from the sector formula from geometry way back when. You might have done this last year in honors pre-cal, but it could easily be something that slipped by you guys. So back in geometry, when you were finding the area of a sector of a circle, you'd have a theta and the radius. And the formula in geometry was theta over 360 times pi r squared, because you have this fraction of the whole circle, right? And so the only thing is that because we're doing calculus, we want to work in radians, not degrees. And so instead, the area of each section is theta out of 2 pi times pi r squared, and the pi's can cancel out, so it's 1/2, and I'm just going to write it a weird way, but trust me, 1/2 r squared theta. Right, that's the formula for each one of them. So the total area would be 1/2, I'll say r1, like this could be r1 here, that distance, that radius, r1 squared times theta 1, because I could use r1 because, well, we'll talk about it in a second. And then plus 1/2 r2 squared theta 2 plus, and so on. But as n goes to infinity, as the number of regions that I have goes to infinity, then it's like, okay, so now they're going to get infinitely small. And so I can say that instead that it's going to be the integral of 1/2. And then each r is going to be its own separate thing as I go around. So it's going to be just r squared. And now instead of saying theta, it's going to be this infinitesimally small little angle. And that's d theta. So here's the formula for the area of inside a curve. So it's like between the origin and the curve, because that's how r is defined coming out of the origin. And so the area is going to be the integral from, I'll say theta 1 to theta 2. And usually people put the 1/2 in front, and then r squared d theta. That's it. That's the formula. Let's look at an example, because, that's one. Find the area of one petal of the curve r equals 2 sine 3 theta. So first I have to figure out how big a petal is on this thing. So this goes back to your graphing of polar graphs. So remember what I said, is like start with 0 and then figure out what you need to do to get back to 0 again. Okay, so at 0, sine of 3 theta is 0. So just thinking about it here. So r and, well, actually I should say theta on the left and then r on the right. So when theta is 0, then r is going to be 0. So I start in here. That's good. And now I just need to figure out, okay, when's it going to get back to 0 again? So sine gets back to 0 when you do the sine of pi. So if I look at this thing here, so when theta equals, that was a weird way to place an equals. When theta is pi over 3, I'm having trouble writing right now. It's kind of late in the day. Then r is going to be 2 sine of 3 times pi over 3. And that'll get me the sine of pi again. So when I get to pi over 3, I'll be back to 0 again. So let's see. Okay, how many do we have? 1, 2, 3, 4, 5, 6. Okay, so it's like, so then this first one right here, that's pi over 6. And the next one is pi over 4. and the third one is pi over 3. Okay, those are the angles that I know. The other ones are like at 15 degrees and 75 degrees. I don't know the radian fractions off the top of my head. So if I think about it, this thing is, this thing is starting at 0, and then it's going to be coming out, and then by the time it gets to pi over 3, then it's back to 0 again. Okay? So, and this thing's going to be symmetric as it goes out, so that means the place where it's going to be the farthest out is pi over 6, right? That'll be, because that's halfway there. It starts at 0, and it goes out, and then it comes back. So pi over 6, so the sign of 3 times pi over 6, that's pi over 2. Awesome, the r is 2. Woo! There we go. Sorry, I'm having trouble maneuvering here. Okay, so what happens is it starts at 0. When you get to pi over 6, you're at 2. And by the time you're at pi over 3, you're back down to 0. This thing's going to look something like, okay, undo that. I'm just going to do it in different color because it's going to be hard to see otherwise. And it's going to look something like this. And then come back in. So now I can see what the bounds of this thing are. The bounds, remember that the integral is going to be the integral from theta 1 to theta 2, 1/2, and then r squared d theta. So 1/2, that's easy. Sorry, that's just kind of stupid. All right, integral. But now I know the bounds because I figured out what the curve looks like. It goes from 0 to pi over 3. Yeah? And that'll be 1 petal. And then I need to know what the curve is. Well, the curve, they give me the function right here. I mean, I could put r there, but remember, it's going to be d theta. And so in this case, it's going to be r squared, which is 2 sine of 3 theta. That's just r squared, d theta. Perfectly doable integral, except because of chain rule issues, it's not a easily doable integral, so this would be a calculator one. But this would be the setup for it. So I'm just doing the setup right now. I'm not worrying about doing the integrals. Ooh, I got kind of dim there. Is my battery getting low? Battery's getting low. So what did I need to know? I need to figure out what the bounds were, and then I just need the formula, 1/2 r squared d theta, and then just plug the function in. Okay, it's not too bad. Okay, here's an AP problem, and we'll go over how to do it on the calculator in just a second. And so the graph shows a polar curve, r equals 2 theta plus cosine theta for 0 to pi. Now me, when I start on this, like I said before, I like to first take a moment and just plug in some numbers so I figure out what this thing looks like, so I understand why it's looking the way it's looking. So let's start off with theta being 0. When theta is 0, then r equals 2 times 0 plus cosine 0. Okay, so it starts right here at 1. And you might be like, Mr. Ellinger, that was obvious because that's 0. But remember, you get negatives. You could have a negative r at some point in time. And so like the curve starting over there could be on the negative part of the curve or something. It could be something funky. So I just want to plug in 0 to make sure it works. And then I could plug in another value. Like I plug in pi over 2. So cosine pi over 2 is 0. And so r would be 2 times pi over 2, which is pi. Oh, it's 3.14. Oh, I get it. And then when it's out here, it's at 2 pi, because if r is pi, or 2 pi minus 1. Because if r is pi, then it would be 2 times pi plus cosine pi, which would be 2 pi minus 1. And so it's 1, 2, 3, 4, 5. Yeah, because 2 pi would be 6.28, so this is 5.28. All right, I totally get it. This is starting at 0 and then going to pi. Got it. What is the area of the region bounded by the curve in the x-axis? So what's the area of this region right here? Piece of cake. It's just the integral. Go ahead and why don't you set it up? I'll get my calculator open while you're setting it up. Of course, that means the calculator is going to open on my screen and make things hard to see, right? Okay. See, there it goes. So it'll go in a second. So you've got your integral set up yet? It's pretty straightforward. Now that I understand the curve, come back. I want to go back to that. There we go. So it's from 0 to pi 1/2, and it's just r squared, so that's going to be 2 theta plus cosine theta squared d theta. Now I got to do this on the calculator. Now, here's the truth about doing this. Now, keep in mind, this was a calculator problem, is that you've got two options of how to do this. One thing you could do is you could, now I'll go into calculator, you could go and go into your mode and switch it to polar mode and do the whole thing in polar. So I could go over to polar, say, yeah, I want to do it in polar mode, and then notice how now the y equals is going to be r equals. So I could graph it, 2 theta, now that's a theta, plus cosine theta. And so I could check the graph to make sure I liked it. I personally think this is kind of a waste of time on this one because I don't think we need it, but okay. And we only wanted it from 0 to pi. Don't worry about those points. That's from math team. So we only want it from 0 to pi because that's what the problem said. So I can go from 0 to pi. There we go, and graph. There we go. There's my curve. And now I could do the integral by doing math 9, and plugging it in here. But while you can do that in theta, I didn't really need my calculator to graph this thing. Like, I figured this thing out without having to actually graph it myself, like without having to use the calculator to graph it. And so really, I could just do this whole thing in x's. Like, these are just variable names, and x's or thetas are going to be the same thing. It's just a letter. All it is a letter that's sitting there. And so this is exactly the same as 1/2 integral from 0 to pi of 2x plus cosine x squared dx. It doesn't represent the actual x's here. I'm just using x to stand for the variable, whatever the variable is. So now I'll do it that way. And so that would, to be honest, that's how I would do the problem. I'd only go into polar mode if I thought, man, I do not understand this curve. I need to graph it so I see what it looks like. So just go into y equals, and we can put the curve there if we want to, and do it the shortcut way I showed you, 2x plus cosine x. Close it off just for aesthetics. Mode, I'm in radians, awesome. And so I want to math 9 it. And it's going to be, and I'm going to forget, so I better make sure I don't forget my 0.5 sitting in front, right? Just like you don't want to forget the pi on that last one. From 0 to pi of, and now I can, this is where that putting it in y1 helps me out. I could just put y1 and squared dx. So either one is totally fine. You can define it in polar, or you could define it here, either way. But if you want to see the actual graph, you'd have to be in polar. And that looks good. 17.456. We look at the answers. Yay! And we got it. Okay. All right, we're going to do some more. So stay tuned. I'm going to stop here just because it's a good break, I think. Let me just see. Oh, well, you could set this up. Why don't you set this up, and then we'll look at it. We'll look at it next. Yeah, take a second to think about how to set this up. It's a little tricky. So maybe just try to set it up, and then we'll talk about it. Okay, next video.